Okay, welcome. Thank you for coming. So, today I will tell you a little bit about the Cooper pair and the coherence length. And then this famous result that 2 delta over kBTC is 3.53 in BCS theory. And I will tell you how we can get other than S-wave pairing. Because in BCS, the pairing is isotropic. I mean, if you look at the order parameter, this quantity does no K dependence. But in many materials that have remained difficult to understand, there's some momentum dependence to this thing, and we will see why. I will show you. And I will discuss the spectral weight and coherence factors. The fact that in BCS theory, the quasi-particles are linear combinations of electron and hole. So, and that has consequence of many observables. So that's coherence factors. And then I will tell you about the BCS wave function. I will make a summary of the class. So you don't need to give any notes today, because it will be rather fast, and there's a part of the course like this that is not in. I have not managed to put in the notes yet. They will be there eventually, but they are not there. So, what did we do? So, if you look at this piece here, it was in our Hamiltonian, it was sandwiched between the psi and psi dagger, where psi and psi dagger were non-boost spinners. So that was our guess for the broken symmetry state. So in other words, we allow the off-diagonal components in the G of K. Why? Because we saw that if we look in the normal state and you take C dagger at some time and CC at some other time, then if you look at the zero frequency, that's a thermodynamic quantity, diverges at some temperature. So that's the transition temperature, and that indicates to us that there's an order parameter which will make this non-zero. So then what we say is that, okay, we have H0 tilde that had this psi dagger. Now we ask the full, we have to remember that the full K is really K0 tilde plus K0 minus K0 tilde plus V plus some interactions, right? So this is my non-interacting, this will give me my non-interacting Green's function, and which is this, once I have assumed this K0 tilde, this is G. G minus 1 is easy to find with this. And the K minus K0 tilde is here. And I do the R3-Fock approximation here. So I put the Green's function here, and there's an interaction. And I ask that this self-energy for the affected medium at the R3-Fock level is 0. In other words, there's no, whenever I work with BCS, I don't put any R3-Fock corrections. They are cancelled by this. There are still residual interactions. There are still Goldstone modes and so on and everything. Another way to do that is with oh my, okay. The other way to do that is with is with the variational principle. That may be a little bit more satisfying, but anyway, it's important to understand these that there are residual interactions. Okay, so now I want to show you that discuss the coherence length. So if I look at this thing here, this piece of the Green's function, it is given by this, right? So this now is equal to this. So oh, and I forgot the gap. Yeah. So once you do this for the off-diagonal components, you get this gap equation. That's the gap equation for BCS. Now, if we compute this thing minus time ordered product of C dagger K up. No, not C dagger C. CK up C minus K down. Then it's equal to T times the sum over Matsubara frequency, IKN, of this delta. There's only one delta. We said that delta, the equation for delta 1 and delta 2 was identical. So we choose just a phase such that delta is this. So sum over IKN of delta of K. Okay, in BCS, we take delta independent of K in the simple BCS approximation, divided by 2 EK times 1 over IKN minus EK minus 1 over IKN plus EK. Okay, if I put this on a common denominator, it gives me this denominator. Yeah. Now I can do the sum, so it will be minus Fermi function. So I have delta over 2 EK, and I have Fermi functions. F of EK minus F of minus EK. And this is 1 minus F of EK. So all together, this will be plus, and this will be 1 minus 2F, and 1 minus 2F is hyperbolic tangent. Okay, so at 0 temperature, we're looking at EK is always positive. So at 0 temperature, beta goes to infinity. So I can replace this by 1, and that's my pair wave function. Okay. Now, if you look at at 0 temperature, I replace this by 1. And if I want to do this in real space, I just have to take Fourier transform. Huh? So I have just to take integral d cubed k over 2 pi q e to the I k dot r minus r prime of this guy, and see what it looks in real space, what it looks like in real space. Now this EK is square root of zeta tilde k square plus delta square. But this is what? That's the energy measured with respect to the Fermi energy. And we are looking always in BCS, we are looking at wave vectors that correspond to energy within a shell equal to the Debye frequency. So it means that here I have to go to, I can write VF delta K delta, well, I don't want to confuse things, so let me put a small delta here. That's deviation. Oh my God. This is deviation with respect to the Fermi wave vector. So I have VF delta K square plus delta square. Now I can put this here, so I have one here and one there, and delta here. So now you see there would be a part, this K is equal to K Fermi plus delta K. So there's a rapidly oscillating part, and then there's a Fourier transform with the delta K, and it has a spread in delta K. You see the function here falls when delta K is equal to delta over VF. And as you know, there's a width in K space, there's a width in real space. So the width in real space will be C0 will scale like, I mean, one can do a real calculation, but here I just do the simple Fourier arguments. And that's called the coherence length, this K0. Okay. So now, what about this TC and delta 0? Okay, the way we get TC and delta 0 is that we replace this V just by minus a number. This is an integral you can replace by integral over energy with the density of states. We take the density of states constant, and then you have just these integral over, so in the end, what you get I don't know why it's so hard to erase today. So what you get here is integral the epsilon density of state at the Fermi energy, and you get so just the absolute value of a constant and then a plus sign, and integral over epsilon, you get 1 over 2 epsilon, so you get delta over 2 square root of epsilon square plus delta square, and this hyperbolic tangent. So to find TC, all you need to do, and this is equal to delta. So to find TC, all you need to do is to put delta equals, simplify the delta and put delta equals 0 here. Then you see you have just 1 equals something. And that integral over epsilon will have this hyperbolic tangent divided by this epsilon square divided by epsilon. So there will be a log, and you will find the TC. And if you want the 0 temperature, then at 0 temperature, what you do is that you replace this by 1. And again, you can do this, this integral. And you see in both cases, you have this quantity that comes in. So for example, for TC, you find that TC is order, well, there's a numerical constant, 1.36 times omega dBi times exponential of -1 over u0. omega divide. So, and there's some similar structure for delta. So the ratio is this. But most importantly, there's a TC, and you see that if the it is generally you have omega d, so TC you say should be of order omega d, but no, because this here involves U0 and the density. I'm sorry, it's not omega d here, it's the density of states. What am I doing? Density of states. So that's like 1 over Fermi energy. And this is small. So the exponential here has a large argument. So the TC is much less than omega divide. Okay. So this is an example where you see that the simple perturbation theory would not have allowed you to cross the transition temperature because it's really non-analytic in the perturbation here, V0. Okay, so what do I mean by these coherence factors? Well, take this Green's function, analytically continue to the real axis, and then take the imaginary part. You see that the G retarded is has omega here and these denominators. So let me take just the 1,1 component that corresponds to a spin up, that corresponds to C dagger up. So it's the usual Green's function, this piece here. So if I look at just this, the retarded piece is omega. So I need to look, there's a 2 by 2 matrix. I need to look at the top row. So I have omega plus zeta k. And here I have 2 ek, and rewriting the denominator. 1 over omega plus I eta minus ek minus 1 over omega plus I eta plus ek. I did not put the plus I eta here because it doesn't, doesn't lead to anything. So now if I look at minus 2 times the imaginary part of G retarded 1,1, that's equal to the spectral weight for upspin, A of k and omega. And you see that it's equal to, here this will be ek, so I will have 1/2 the ek simplify of 1 plus zeta k over ek, delta of omega minus ek. And then I have this, so minus 1/2. Now omega is equal to minus ek, if when I take the imaginary part. So it will be minus 1 plus zeta k over ek, delta of omega plus ek. So I would put plus and minus. So you see there are 2 poles, one at positive energy, the other one at negative energy. And when zeta k is, when k is large, much larger than k Fermi, this becomes large, and then this ek will also become equal to zeta k, right? Because Ek here is zeta. I forgot the tilde. Ek is this, right? So when zeta k is large, when we are far from the Fermi surface, this becomes 1 and this goes to 0. So for k larger than kf, it looks like electron. Now, if in the other case, when you are at zeta k that's very negative, then this ratio becomes 1 minus 1, so that disappears, and this is survives. So the spectral weight has two bumps like this. This is for k larger than kf. And the quasi-particles are linear combinations of electron and hole. Okay. So in other words, we have diagonalized the Hamiltonian. We have now new creation and annihilation operators. This is our diagonalized Hamiltonian. This is our diagonalized Hamiltonian. And there's a unitary transformation that goes from the Nambu spinner, Ck up, C dagger minus K down. It goes from this Nambu spinner to this these quantities. Okay. So these prefactors here are called coherence factor. They are just basically what happens in these are simply the coefficients that go in the canonical transformation. So you can check that. So let me call this UK square. And this is VK square. And the canonical transformation looks like this. So in the case of the triplet, by the way, in the case of the triplet, the spins are parallel. So when you are at the Fermi level and I erase this, but the two coefficients become equal to 1/2. The quasi-particle are their own antiparticle, and it's called the Majorana particle. So if you've heard of that, it's just a special case where the spins are parallel. So Ck up, C dagger minus K down is equal to UK minus VK, VK star U star K. So you can check that this matrix is unitary, and that's the most general 2x2 unitary matrix you can write. And here I have gamma K 1, gamma dagger 2, gamma 1, not gamma dagger, gamma. So I stay in the Nambu notation if you want, where this is a destruction operator. But you see that there's these Right. Okay, it's clear that this thing is given by the inverse of this unitary transformation applied on this. And so if you do this little exercise with the of expressing C in terms of the gammas, and then if you take that, gamma dagger, gamma will be the usual canonical anti-commutation relation, so that this is related to a Fermi wave vector, to a Fermi function, and gamma is 0. You get to exactly this this thing there. So whenever you do some experiment, it's done with real electrons, right? So you come with the C and a C dagger. But when you get in the superconductor, it's the quasi-particles that are the real excitations. So there will be, it will modify all the measurable quantities. And what will come in are these coefficients here, these coherence factors. This value I gave you earlier. Now you see that the UK square I'm sorry, there's a bug here. I forgot to take some tissues to erase, and this one is getting really bad, so I have to fix it for a moment. So given what I had written there earlier, we'll find that UK is a phase, e to the I phi. That could depend on k, but in fact, once you rewrite the delta in terms of the u's, you see that the u's and the d's, and you use the argument that I mentioned earlier about phase coherence, you will see that this cannot depend on this phase cannot depend on k. And then we have 1 over square root of 2 times 1 plus zeta tilde k over e k to the 1 half. And for v, it's the same thing with the minus. Now, how do we get the BCS wave function? The BCS wave function is obtained by filling all the negative energy states. You remember that the gamma, there was a plus E and a minus E, and you can see it here. So you fill all the negative energy states. So the negative energy states were the gamma 2. And then you don't act on the vacuum, you act on the vacuum of the Nambu spinners. But the Nambu spinner is a C and, sorry, it doesn't look so nice. The Nambu spinner is a C and a C dagger. So the vacuum of the Nambu spinner has a filled Fermi C of down electron. So you have to fill not only the Fermi C, but every state in the Brillouin zone with with down electrons. Okay. In other words, that was the vacuum of the normal state. That was the ground state of, the vacuum of the normal state. That's destroyed by the Nambu spinner. And then here you fill the negative energy states. So you see the gamma dagger is a combination of C and C daggers. So when the C are anti-commuted with the C dagger to destroy the vacuum, there will be some 1 that will come. And then there will be some C dagger that will survive. So the final expression for the BCS ground state is this. Times this guy here. So in the ground state, not the general thermal state, but in the ground state, you see that you will have states with different numbers of particles. Okay, so it's a linear combination of states with different number of particles. So we broke a symmetry, and the symmetry we broke is total charge conservation. Within locally charge is conserved. I mean, everywhere in the system, the charge is conserved. But you can add, like in the ground canonical ensemble, you can add and remove a certain number of electrons, and the overall phase here, because this U and V have a phase, it has to be the same phase by the BCS equation. It has to be related. I mean, there has to be a single phase here. It cannot be dependent on K. And that phase is the phase that corresponds to the breaking of the total charge conservation. So there's a theorem that's called Noether's theorem, where every continuous symmetry has an associated charge conservation law, and here gauge invariance, or the fact that changing the phase, is related to number conservation. So another way to rewrite this is to factor the U here, U star of K, and then divided by U star of K, and then this, given that the square of the creation operator is 0, I can write this as exponential of plus Vk over U star K, C dagger minus K up, C of K down. And in doing so, we don't gain anything. I mean, it's just another way of rewriting the same thing. But if you know about the coherent states for bosons, this is like a coherent state, no? So for bosons, if you have a B dagger, we would write a B dagger here, just one operator, B dagger, and that would be a coherent state. So for example, for light, for the electromagnetic field, just the ordinary electromagnetic field that we know, where the classical field here, in terms of photons, it's a coherent state. In other words, it's a superposition of states with different number of bosons.
I'm sorry, I have a question.
Yes.
Where does the C in the exponential come from?
It's an
the
error.
non-dagger.
It's an error.
Okay.
It's an error.
Thank you. Okay.
A very important error. Yeah. Very bad error. I should lose all my points here. Okay. It's a C dagger, C dagger. So that looks like a boson because it has two two fermions. Okay. I'm sorry, that was a little bit fast on BCS theory, but I assume you have seen it in other classes. I mean, it's just another way of redoing it within this formalism. The only thing I need to tell you now is what happens if there are repulsive forces. Okay. So suppose, so in high temperature superconductors and other unconventional superconductor, what you find is that the pair wave function is not S wave, but it can be, for example, D wave. So how can that come about? Well, suppose you have, instead of having phonon here, you have a spin wave. And suppose that spin wave is, is an antiferromagnetic spin wave, so it is peaked at the wave vector pi over A, or pi over A, where A is the lattice spacing. Then what will happen in this equation is that this thing will be maximum when k minus k prime is equal to pi. So what does that mean on a lattice? It means that suppose I want to know the gap. I have the Brillouin zone here. I'm on a lattice, so the Brillouin zone is has a finite extent. And suppose I want to know the gap here at this point on the Fermi surface. Okay, I have some Fermi surface. And I want to know the gap here. Then when I do this integral, it's the pi. This is a repulsive force. So it's repulsive. And I have a minus sign here. So I have to, I mean, everything else is positive. So how do I solve this problem? I solve this problem because if I go from here to there, I need minus pi to do this. So it's the same wave vector as this. And you see, if this delta k prime changes sign when this is large, then I'm okay. I get rid of this minus sign. Okay. So in other words, if I take a gap function that is, let's say, positive like here and negative there, it will change sign and it will be enough to get rid of this minus sign here. And the advantage of this is that also in a D wave, the wave function, the pair wave function gets to 0 at the origin. So if there are strong repulsive forces, you can avoid them this way. Okay. So that's a very simple-minded, but I think essentially correct way of thinking of pairing, at least when the interactions are not too strong, in systems that are purely repulsive forces. Okay, so now I'm supposed to summarize the course in 15 minutes. So if you don't mind to stay another 10 minutes, perhaps I can can do it. Okay, so we started by asking what do we measure? What we measure is scattering experiments, our correlation function, for example, the spin-spin correlation function. And instead, if I look at linear response, so the response to some external field like the electromagnetic field, or the vector represented either by a vector potential or by some Zeeman coupling or whatever linear response quantity, then what I have is instead the theory for linear response. So in scattering experiments, I measure, for example, let me put an index I here, but that's like a wave vector if you want, and a function of time and a j, and we take the Fourier transform of this. And the Fourier transform of this corresponds to some energy, omega, dt. And so that's, and this I found just using the golden rule, okay? Golden rule, and then the Heisenberg representation for time evolution. And this would be, for example, we could this S AI J of omega in the scattering experiment. Now, if we do linear response, to some external field, let's call it little ai, that's my external field, that's a function of r and t, and some operator like this, let's say, well, let's call it j of r and t. Then using just linear response, I get a susceptibility. So here for this, the response to this, I get that the change in AI due to some coupling AG is equal to chi AI AJ of omega times a little aj of omega. So that can be all wave vectors, q everywhere. And this is the retarded function because it's causal, right? It has to come afterwards. So this chi ai aj of omega of t of omega, sorry, retarded is as a because it's retarded, it obeys Kramers-Kronig relation. Omega prime over pi, chi double prime ai aj of omega prime divided by omega prime minus omega plus I eta. Okay, and this quantity chi double prime is related to dissipation, and it is really what this is the spectral representation. This is really where the physical information is. Why? Because chi double prime ai aj is equal to 1 over 2, there's an h bar there, times the commutator of ai at time t times aj. So that's at time t. And that's the Fourier transform here, aj. And it's easy to find a Lehmann representation for that. We have used the Lehmann representation all the time, everywhere, to find the relation between various quantities. And this chi double prime is related to this. So in other words, this is equal to 2 over 1 minus e to the minus beta omega times chi double prime ai aj of omega. So basically we can focus on this for many, many things. And then in the end, if we do a scattering experiment, we can go to this. And this has a nice representation. Now you see that at t equals 0, this is equal time commutator. So they are usually easy to compute, the equal time commutator. So it means that the integral over frequency of this, over the integral over all frequency gives equal time results here that is easy to compute. So if I take a time derivative here, it's a time derivative, and I evaluate at t equals 0, again, it's easy to evaluate. And what will the time derivative do? Well, the time derivative 2 will be like including some additional omega here. And the most famous sum rule we have used was the F sum rule. Now, the problem comes when you want to do calculations, right? If you want to do a calculation, then these operators, like the density operator or the spin density operator, the physical things that we see are bilinear in fermions, right? It's psi dagger psi. So basically, in the end, what we do is, what we need is we need to compute quantities that, for example, in this case, there are two, there's psi dagger psi here, psi dagger psi here. So there are 4 fermions. And in quantum mechanics, the particles have the bad habit of doing all sorts of crazy things, right? Like going from here to there by going through all possible paths. So we have to take that into account. And so it means that we need to know how to compute correlation functions for Green's function. Where Green's functions are just the same, essentially very similar to this thing, except that they are for field operators or creation annihilation operators instead of being for density or spin density. All along we have used the second quantization. I'm not going through second quantization again. It was sort of our basic tool. So so we also need to know Green's functions, and there's the analog of this, which is the spectral weight. Okay? Now it's confusing, I realize now, because this is an operator and here it's different. It's the spectral weight. That's more the analog of this. Aij of t is equal to the expectation value of the anti-commutator of psi I, where I can be wave vector, position, anything, I don't care, of t, and psi j dagger of 0. And these expectation value, remember, are always, I should have said from the beginning, this of some operator O here is just trace e to the minus beta h minus mu n times O, where trace is the trace over all energy eigenstates of this. Or since the trace, you use whatever basis you want, divided by trace e to the minus beta k. Okay. Now, the Green's function here is related to this in a way very, very similar to this. It's like a response function. So it's gr of ij is just equal to n of omega. It's just equal to integral d omega prime over pi, 2 pi in this case, because here we have the 2, here we don't, aij of omega prime, and then here the omega prime plus I eta, omega plus I eta goes, and the sign is switched here, omega prime. Okay. Now we look at how are we going to do any calculation, and we realize that we need perturbation theory, and we need perturbation theory not only for these looking at what happened to these operators, but in particular because this when I write e to the minus beta k, there's a piece that I can diagonalize, and there's a piece that I cannot diagonalize. Okay. So, fortunately, when we do perturbation theory, we do the interaction representation, and we realize that we can do everything in imaginary time, and then analytically continue. In other words, we can define a chi ai aj of I q n of tau to begin with. Tau as the time-ordered product of ai of tau aj. And that's the time-ordered product comes here because if you look at the interaction representation, the time-ordered product occurs very, very well. I mean, it's very natural to express it like this. Now you realize that this has periodicity condition in imaginary time because these are traces, and the evolution operators are just e to the k tau, e to the minus k tau. So it's the same operator as the density matrix here. So this is as periodic boundary condition. So you can do a Fourier expansion over the interval from 0 to beta, and then you realize that you can write a chi of Matsubara here, IQN. That is just simply related to, here I put this backwards, sorry, it was omega I eta minus omega prime. No, I had it correctly, sorry, it was correct. So here it's omega prime minus IQN, okay? So because of this nice property, we can just work with in Matsubara, very simple, and then do the analytic continuation. And here we discover that if we define g of tau as a minus time-ordered product of psi of tau of some ij of I psi dagger j. Now this has anti-periodic properties over the interval 0 to beta. So that means that we can expand in odd Majorana frequency. Here the Majorana frequency IQN were equal to I times 2n times the temperature, and here it will be I 2n plus 1 times the temperature. And that all that will occur is that we will have IKN here. And IKN. Okay, so that's the starting point, if you want. Okay, now we need to do, to do some model and solve some models. So the first model we looked at, I mean, I'm skipping the layman representation, but the layman representation is the easiest way you have to relate these quantities in imaginary time to these scalable prime, and it's A that are the basic quantities. And I should add the very important result that in general we parameterize, I mean, the Green's function we write like this. We write that the G of IKN, let's take a translationally invariant case, is 1 over IKN minus some dispersion relation minus sigma of IKN and some K dependence like here. So that's the self-energy. And once you analytically continue and look at this, the Fourier transform of this, you find that the A, let's take at the translation invariant case, A of K and omega, that you can measure in a photo emission experiment is minus 2 sigma double prime of omega minus epsilon K minus sigma prime. So that's the imaginary, that's the real part, plus sigma double prime square. Okay, so the sigma is in some way giving width to the particles. Okay, so now we need to compute these quantities. So the way we developed the perturbation theory is by using a generating functional formalism. So we said Z of phi is equal to the trace of e to the minus beta k times the time ordered product of e to the minus psi dagger 1. Well, okay, I think you will not see this if I continue writing like this, so I will move to the line above here. I add e to the minus psi dagger 1 bar, phi of 1 bar, 2 bar, psi of 2 bar. Okay, so this goes here. And then you see that I can, if I take the functional derivative of the log of z with respect to phi 1, 2, and we said that the nice thing about time ordered product is that when we have numbers here, we can differentiate just as if it was an ordinary exponential. So phi 1, 2 will be equal to minus g 2, 1, where g is defined just like this in the case of the time imaginary time formalism. And then I want not only the Green's function, but I want also quantities like like this, because in the end, I want to compute the density correlation function, for example. So I can do delta log z square, delta phi 1, 2, delta phi 3, 4, and that gives me the expectation of psi dagger 1, psi 2, psi dagger 3, psi 4, and then I have to be careful that there are Green's functions. I mean, there is a z is in the denominator, right? The functional derivative of log of z. So there's z. I need to functionally differentiate z as well. So there's plus g 2, 1, g 4, 3. Okay. So then the rest is the rest is not too complicated also. So now again, always working in the Majorana formalism, I can find out that g minus 1 is g0 minus 1 minus phi minus sigma, where sigma times g, I will not write all the indices here, but sigma times g came from the equations of motion, right? I took the time derivative, and sigma times g was basically v times psi dagger psi dagger. So it's a 4-point correlation function that comes here as well. So that's the definition of sigma here. If I define it like this, I recover the form of the Green's function that I mentioned earlier. Now to find these 4-point functions, what I do is just that I take the functional derivative with respect to phi of g times g minus 1, and that gives me that I will run out of space. So it gives me that delta g delta phi times g minus 1 plus g delta g minus 1 delta phi is equal to 0. So that delta g delta phi is equal to minus g delta g minus 1 delta phi times g. And g minus 1 I have here, so I can functionally differentiate with the phi here. So that gives me the gg. And when I functionally differentiate with respect to sigma, instead of writing delta sigma delta phi, I write delta sigma delta g delta phi, and I have times the g. So the g is attached to the sigma here. Okay. Then how do I do the electron gas with this? So that's our first example. So to do the electron gas, I start by looking at the first piece of this. That was the Lindard function. So that's in the non-interacting case, right? And okay, I find that there are regions of frequency. Let me see, running out of this again. There are regions of frequency where chi double prime is non-zero. So there are some absorption, and that's all very nice. But in the end, I also want to know more about that. I want to know the interacting, what happens in the interacting case. So in the interacting case, I have to put the Coulomb interaction to compute the density correlation function, and extract, for example, the dielectric constant that will tell me about screening. So screening is one of the most important things we learn from the electron gas. So how do we get to this? Well, we say that, okay, I will do the simplest approximation for this. I will take the R3-Fock approximation. So for sigma, I take the R3-Fock approximation, which basically amounts to factoring this thing here. So if I do this, see, I have an expression for sigma in terms of G because sigma was related to this 4-point function. So if I do this, then what I get for the susceptibility, for the charge, the density correlation function. So n of the q and omega is chi 0 n of q omega divided by 1 plus the Coulomb interaction, the bare Coulomb interaction, times chi 0 and n of q and omega. And what I find now is that is this basically screening. So the chi and n here, when omega goes to 0, the dielectric constant is what is in the denominator. We showed that also. So the dielectric constant will be such that that epsilon, okay, v of q, which is related to e square over q square epsilon, will go to e square times here it was epsilon 0, q square plus q square Thomas Fermi. So as omega is small, we have screening. But on the other end, if q goes to 0, and we look at finite frequency, then epsilon becomes epsilon 0. Again, epsilon is this denominator. And we prove that is epsilon 0 times 1 minus omega square plasma divided by omega square. And so it means that the dielectric constant goes to 0. So it means that we have oscillation at the plasma frequency. So when omega is equal to omega plasma. So, and when we look at the F sum rule that we derived from commutation relation, we find that this plasma here suffices to satisfy the F sum rule. So that's what we learned from the electron gas mostly. I mean, there's also Friedel oscillations and there's all sorts of things, but the main thing is screening and plasma oscillation and satisfying the F sum rule. Okay, then we go to fermions on a lattice. So fermions on a lattice, the same thing here works. The difference is that we have an interaction U now, and we find that for the charge fluctuation, if we use this exactly the same scheme with the R3-Fock, here we get. Oh, I forgot to mention. Oh my God, very important. The other lesson for the electron gas is that we need to use the screen interaction. So instead, the R3-Fock result is completely crazy for the electron gas. So for the self energy, we need to put here the Coulomb interaction but the screened Coulomb interaction. So divided by epsilon of Q and omega E square divided by epsilon of Q and omega epsilon 0. 1 over Q squared. So if we do that, then we get this the so-called GW approximation in ab initio methods, and we get reasonable results. Now we go to fermions on a lattice. And for fermions on a lattice, what we find is that the RPA, what we did for the electron gas, so here we would have U over 2. RPA gives a crazy result because it does not, well, this is for charge, and the new quantity that we get is that spin fluctuations become important. And that's because of the Pauli principle. Yeah, I don't know. Let me, it turns out the chi0 is the same. So that gives a phase transition in 2 dimensions. So it violates the Mermin-Wagner theorem, and it also violates the Pauli principle in the sense that with this approximation, if you look at n up times n up, it's not equal to n up, but it should, because n up is 1 or 0 for the if we have a single band. So we fix that by having U charge and U spin that are determined in such a way that the Pauli principle is satisfied, and that U spin is equal to U n up and down divided by n up times n down. And using the charge and spin sum rules. So if I sum over all Q and all Matsubara frequencies here, I should get, for example, for the spin, I will write it for the spin. If you sum over all Q and all Matsubara frequency, on the right-hand side, you get n up times n down. I'm sorry. You get n up plus n down. So you get the total density n minus 2 n up and down. So if you substitute this here, you get a self-consistency equation for n up and down, and that's the 2-particle self-consistent approach, PPSC. And for the self-energy, then we do just like we did with the electron gas. We take these susceptibilities, U spin, U charge, and just compute the self-energy. And that can give a pseudo gap, for example, in the case of antiferromagnetic fluctuations. This is what happens in electron dope cuprates, for example. Okay, so now broken symmetry. That's the last topic. So if we just look at what I'm erasing now, in the case of Q equals 0 in 3 dimensions, we find that in the normal state, this uniform spin susceptibility diverges. At some temperature or some value of U, depending. I mean, at 0 temperature, the criterion is U minus single particle density of states is equal to 0. So we fix that by breaking the symmetry. And so in other words, we give a net magnetization. So broken symmetry, you can see, comes from, you can put some small stray fields and then let them equal to 0 at the end of the calculation. So broken symmetry occurs in the infinite volume limit, where you cannot interchange the order of limits. And associated with that, there's rigidity. In other words, the spins will all be aligned. And there's also a Goldstone mode. So if the symmetry is continuous, you can restore it like this. So we saw that the transverse susceptibility, then we did the calculation in the broken symmetry state that we found in the same way as the BCS here. And in the broken symmetry state, we checked that the transverse spin susceptibility contained the Goldstone mode. And finally, we looked at superconductivity, where again we have a susceptibility that diverges in the normal state, but it's in the particle-particle channel. And we use the same formalism here to see that divergence. And in the ordered state, we just broke the symmetry by allowing pair wave functions to be different from zero. Now, if you look at what happens to the plasma frequency, to the Goldstone mode, well, it turns out the Goldstone mode is killed by the long-range forces, and it's at the plasma frequency. So I did not have time to show, but there's still a Goldstone mode, and it's called this mechanism is called the Anderson-Higgs mechanism, and it's used in elementary particle physics. That's with the Higgs bosons. I mean, it's basically the same concepts that apply in this context. So I did not have time to show all of this nice physics, but yeah, so you could have come just for this last half hour and you would have known everything there is to know. So are there any questions? Okay. So Monday, I will treat some other advanced topic, as I said, and it's you don't need to come. It definitely will not be related to what is in the exam. And if you have any questions during the week, you just write me an email. Otherwise, I will see you next Thursday morning for this. I'll go through the exam, the last exam with you, and answer any questions you may have. Okay.
I have a quick question.
Yes.
So could we have the last exam before Thursdays to try it by yourself, or do you want to do it live with us?
I don't know. The exam of last time, you can do it right now. Yeah, no problem. But I will. I mean, it's not in English, so I will on Thursday. I will start by doing, sort of going through the. I think the last questions are just calculations, so you can, even if you don't speak French, you know basically what's the question. Perhaps I can translate these two, and the other ones they are very short questions at the beginning. So if I have time, I'll translate it in English, but I just wanted to discuss it on Thursday with other people. So yeah, I mean, you're looking for the.
Is it on the class website or in the notes or?
For the exam?
Yeah.
The Friday exam.
No, the last exam. Is it disponible?
The last exam, I mailed it to you yesterday.
Okay, well, I didn't see it. I will. Thanks.
Okay. Okay, if you don't find it, just perhaps I forgot you in the list, but in principle, I sent it to everyone. You see it? Okay, anyway, if you don't have it, ask me and send me an email and I will send it to you. Okay. So thank you for your patience for this very long class and for coming through all the classes. and we'll see you next week. Bye. I'll stick around if you have some questions right now.